Okay, in this lecture, we are going to see two more examples of using templates in C++, and we are going to see two search algorithms. This is going to be, another example of seeing templates in action, and also these two search algorithms are important for us later on because whenever we have a data structure that contains some kind of data, we want to know how quickly we can look up an element in that data structure to see if that element exists there or not, and if it does, where. And these two algorithms are going to be our first introduction to this search kind of problem. So the first search algorithm that I'm going to talk about today is called linear search. So linear search. And the idea of linear search is very simple. So the input is a sequence of values. Okay, so let's say it's an array that contains some values, let's say integers, for example. So have these different positions in the array, and the indices 1, 0, 1, 2, 3, 4, 5, 6, 7, 8. So in this case, my array has size 9. The indices start from 0 all the way to 9. And then the values inside have some values there. Let's say, for example, here I have 10, here I have 7, 21, 32, 2, 9, 8, 1, and 71, for example. Right. So this is part of your input. Is the array called, let's say, A. And then you have a target value. It's called a T. And that's the value that you're looking for. Let's say in this case, the value that you're looking for is 32. So the problem is, it's a search problem, which means that given the sequence of values, in this case integers, and a target value, 32, figure out whether or not this value exists or occurs in the sequence. And if it does, tell me where. So that's the problem. And linear search solves this problem in a very straightforward way. So what it does is that it compares the target value with the first value in the sequence. So are they equal? No. So go to the next one. Compare the target value 32 with the second value in the array. Are they equal? No, they're not. So move on to the next one. Compare 32 with 21. They're not equal. To move on to the next value. Compare 32 with 32. They match, so we return the index at which we found the target, which is 3 in this case, right? We found 32 at index 3. Now, on the other hand, if the target value was something that didn't exist or didn't occur in the sequence, let's say you were looking for 15. So if we follow the same algorithm, it starts from the first element, compares 15 with the first element, they don't match, compares 15 with the second, third, fourth, and so on. It goes all the way to the last element of the sequence, and it never finds the value 15 anywhere in the sequence. And in this case, to showcase that the search failed to find 15, we return -1. And we know that -1 cannot be the index, any index in the array, because the indices start from 0 and go up from there. So whenever you return, this is not equals, this is -1. So let me fix that. So return -1. So -1. So when we see -1 returned by the search function, we know that we were not able to find the target value in the sequence. Okay, now let's take a look at the implementation of this function. So this is the file from the previous lecture that we had print array function and the maximum function. Now I want to do the linear search. Okay, now let's start with the case where there is no template, and let's assume that our array is an array of integers. So we have int, the return type, and then we have linear search, the name of the function, and it takes an array. So as we said that you're assuming that the array has type int, so int a, and then of course the size of the array, int size, and the value that we are looking for, so int target or t. Okay, now what we do is we say for I equals 0, I is less than size, I plus plus. Now what we do is that we compare the target with a at index I. And if they're equal, what we do is we return the index, right? So you're looking at index I and looking inside the array at index I, and you see a value that is called a at I, and you compare that with your target value. If they match, you say I found it, and you return the index. And if not, you increment I to the next I, and so on and so forth. Now, if we go through this for loop all the way to I equals size minus 1, and we never return anything, so outside the for loop, technically, then it means that we compare the target with a at 0, a at 1, a at 2, all the way to the end, and we never found the target anywhere. So this equality was never true. And in that case, after the loop, we return -1 to show that the search failed. Okay, and then you can test this on different arrays of integers. But if you look at the structure of the code, you see that inside the implementation of the function, there is no place that the array being an array of integers is important. In other words, if this was an array of characters, the exact same implementation would work, or an array of strings, or any other type that we can compare the values, right? So that shows that is a sign that this is a good candidate for using templates, because if I want to define another linear search that searches arrays of characters, then I have to basically repeat the same definition and change the types, a couple of them here and there. So let's see how we should do this change. So first of all, I need the templates. If you remember, type name, some type name, like t. So t is a variable for types. And then instead of saying that my array A has type int, I can change that to type t. The size remains the same. Size is always an integer for an array. And the target, which is the value that we're looking for, if we think that this value should be inside the array A, it must have the same type as the elements of A, which is t. And the return type, since we are returning the index at which we found the target value, or -1 if we don't find it, the index remains an integer. So now we have a linear search function that can be applied to arrays of any type. You don't have to redefine the same function over and over for arrays of different types. So again, if you remember, that was one of the places that we use templates, and last time we did 2 examples of this nature. So here we go, this is linear search. But as we will see later on, this is not the most efficient way of searching an array, especially under some conditions. So let's see if we can do better. The second algorithm that we are seeing today for search is called binary search. Binary search. That under some conditions is going to be significantly more efficient than linear search. So let's take a look at the sequence of elements again, an array. Let's say of size 9. Okay, so indices are 0, 1, 2, 3, 4, 5, 6, 7, 8. So the size is 9, and the values, let me use a different color here. The values inside are like 2, 7, 13, 21, 33, 41, 52, 61, and 87. Okay. Now, one thing that you might see here immediately is that the order of the elements, the numbers in the array, is not arbitrary, unlike the previous example. Right? The numbers go up and down in the previous example, but here you see that the numbers only go up. And that is the requirement for binary search to work. So the requirement for the binary search is your input sequence must be sorted from the smallest value to the largest. Otherwise, binary search will not necessarily give you the right answer. So keep that in mind. It's very important that if you're applying binary search, the sequence or the array must be sorted to begin with. Okay, so this is the array A, and then we have the target value T, the value that you're looking for. And let's say the value that you're looking for is 13, for example. Right. Now, here's how binary search works. The way that binary search works is instead of starting from the beginning of the array, we start from the middle, right from here. We compare the value that we're looking for, 13, with the value in the middle of the array, which is 33. And there are three possibilities. It's either that 13 is exactly equal to the value in the middle of the array. In that case, we have found the search is over, we return the index. The second possibility is your target value is smaller than the value in the middle. And since we are assuming that the array is already sorted, if the value that we are looking for is smaller than the value in the middle, which it is in this case, then there is no way that 13 can occur in the second half of the array because 13 is less than 33, and the numbers that come after 33 are going to be even greater than 33. So there's no way that 13 can occur anywhere after the middle value. And that's a guarantee, right? I don't even need to look at the second half, which means I can restrict my search to the first half of the array. And finally, the third case, if, for example, we were looking for 63, then that value, the target value, is greater than the value in the middle. And in that case, there is no way that 63, for example, can occur before 33, before the middle value, right? Which means that in that case, we only need to search the second half of the sequence, right? And that's why it's called binary search. Every step, we divide the array into two, and then you say, okay, I either need to search the first half or the second half. So let's continue with this example. 13 is less than 33. So we know that it cannot be in the second half. So it must be, if it is occurring somewhere in the sequence, it must be in the first half between these values. And what we do is we repeat the same process. We find the value in the middle of this smaller array, compare the target value with the value in the middle. It's either equal, then we are done. Less than, then we search the first half. Greater than, we search the second half. And you see that here when I say repeat the same process, this means, if you're implementing this, you are going to use recursion. So the natural way to implement this idea of either searching the first half or the second half is making a recursive call to binary search by changing a couple of parameters. We say instead of searching the entire sequence, only search the first half or the second half in the recursive call. Okay, now let's take a look at the actual implementation. Okay, here we are. And again, I'm going to use templates for this one because as we will see, the implementation doesn't make use of the type of the elements that are in the array. So binary search. Now we have the array of type C. We have its target, right? T target, the value that you're looking for. Now here, I need to specify which part of the array I am applying the search for. Originally, at the beginning, it will be from the beginning to the end, but remember the recursive calls, right? So then I say from the beginning to half or from half to the end, and I'm making the recursive call. So these two should be added as two parameters to the function. So I say int begin. So this is where the search, the index at which the search begins, and int end. This is the index that the search ends at. Okay. Now there are it's a recursive function, and there are a couple of base cases. One of them is if begin is greater than end. So if begin is greater than end, we are supposed to start from the index begin and end at the index end. So for example, if begin is 7 and end is 2, it says start from index 7 and go all the way to index 2. But that means there is no element between that because 7 is after 2. So that means in this case, the search failed. So remember, we return -1 in that case. Now we need to find the element in the middle. So let's find that index first. Mid equals begin plus end divided by 2. And this is integer division. So if begin plus end is an odd number, it rounds it into an integer when it divides it by 2. And now we compare our target with the value in the middle. So we say if target is equal to double equals a at mid. In this case, our search is done successfully. We found the target at this index, so we return the index at which the target was found. Now, the recursive case, the first recursive case, is if the target value is less than the middle value. What should we do in this case? If you remember the description that I gave you when I was working on the board, if target is less than the value in the middle, the idea is that there is no way that target can appear after the middle because the array is sorted. So the only thing you have to do is to search the part before the middle value, right? So we say make a recursive call to binary search, and it's going to be the same array A, the same target. And since we are looking at the first half, the beginning is the same. So begin, the same parameter, I pass it to this recursive call, but we don't go all the way to the end. We go to the middle, all the way to the middle. So mid -1, because we've already checked the index mid, and target is not equal to that, because if it was, we would have returned mid here. So there is no point including mid here. So all the way from the beginning to mid -1, apply binary search recursively, whatever it returns, return that. And finally, the last case, I can either put an else here or another if. This is the case where target is greater than the value in the middle of the array. So in that case, I need a recursive call. Same array, same target, but not from the beginning of the array because there is no point searching the first half. So I start from mid +1 and go all the way to end. And that's it. That's binary search. Now, later on, we will see why this algorithm is much faster than linear search, but that efficiency comes at a price, and the price is that linear search can be applied to any array. There is no requirement, but for binary search to work, the requirement is the input array A must be sorted. If it's not sorted, this logic doesn't work.